Today, I will be talking about a specific project that we're doing with imaging. And to keep it a little bit more down to earth, we picked everything that we do for acute stroke imaging, at least in our lab in collaborations with the medical school. What we are trying to do really is trying to push the boundaries of what typically can be done with imaging in acute stroke management. So we'll be talking about 3 projects. The first one is community screening for endovascular stroke therapy. The second one, how we can leverage radiology reports with imaging data, and then retina imaging as a proxy for CT imaging in stroke care. So let's start with the first one. What is the unmet need that we are trying to solve? And I'm trying to move, anyway, sorry. So endovascular stroke therapy, we know that significantly improves the outcomes when coupled with advanced imaging assessment like CTP and MRI. And because of that, current guidelines requires to have CTP of MRI done, in as fast as possible when there is a patient with the acute stroke. However, the stroke systems of care is not able to support this type of imaging assessment for endovascular stroke therapy. So in here you have a map of Texas of the acute stroke care that are done in hospitals that do not have this type of advanced imaging assessment. But what if we were able to use images that are more available, like CTA? So here you have the map where there are acute stroke appearing in these hospitals that can perform CTA. And you see that the colors go down, and in here we had to change actually the color map. So the red goes to 28, here the red goes 1,000 and 100. So it's significantly more available than CTA compared to CTP or MRI. So what we are proposing to do is use deep learning and artificial intelligence in general to learn the same informations of the CTP, so these advanced imaging modalities, with a common image modality, so CTA. So we have a training phase in which we have an algorithm that learns to map between the 2 modalities, and once we have the trained algorithm, we can use it and deploy it with CTA only to find information that are used for endovascular stroke treatment, like stroke size and area at risk. Okay, those are the main ones, but there are other informations. So we started to do this a few years ago, and we have multiple papers that have been published, both in clinical journals and more technical journals. But what I want to discuss about is something that we find pretty interesting, because it really talks about the difficulties of doing AI with clinical data. So when we started. So what we try to do is using the CTA, then we have one deep learning models, and then we try to estimate the image level core size, so the core size on the full image, and we found that we were pretty good. So this is the third iteration of our model. We were getting a AUC of 0.83, which was essentially comparable, or sometimes a little bit better, but essentially comparable of what was done with the standard of care, and better than what would typically an expert would do with CTA alone. So that was very exciting, and we went ahead. But then we moved to the next step. So we tried to find the location. So what are the areas that really are affected by core size? So we tried to create these as a segmentation algorithm. However, when we did that using the de facto standard of CTP, things did not work as expected. So these informations were not good. So our algorithms were not working as expected. And the reason being is because those labels were noisy. Essentially, this is a known fact about CDP-based estimations, even though they are used for clinical care on a daily basis. So what we had to do is trying to create a model that work with weak image level labels, and this is very, very, very common in a lot of clinical imaging or clinical data in general. So we have to take decisions with noisy data, which clinicians are really, really good at, but artificial intelligence models sometimes not that good. So we created strategies in which we have these deep learning models that tries to learn, instead of the pixel by pixel informations in the image, it tries to simulate the overall core volume And then we look at the areas that lead to that decisions. Why? Because if we look at the core volume in general, we saw that in there is not that noisy. While instead, if we were looking at the various pixel by pixel, that's where the noise was. So we developed these strategies called weighted gradient-based segmentations that tries to find what are the features that creates these areas just using the core volume. And for those of you that know deep learning, this is very different than GradCam or similar gradient-based approach. So the results were pretty good. So here we have an example of one image. On the top, you have the input, the CTA image. This you have the standard of care that is done with more advanced imaging in the area of the acute stroke. Then we have our pipeline, and this is the actual ground truth done with DWI, which is the best standard we have, but is even less available than CTP. So then we evaluated that with numbers, and we see that we get dice scores of 0.26 that in a general segmentation algorithm might not seem that good, but this was significantly better than training the state-of-the-art segmentation algorithm on the same area. And what's more important, it was also better than the standard of care, significantly better than that. So because of that, we created, we packaged these in a format that can be used by everybody. And there is a demo that you can go in here on a website. In here we have a video of what this demo looks like. You update your CTA image, and then you have the CTA and the areas of the acute strokes. And then we also have, and I'll move forward, a viewer that then you can use to show where the acute stroke is. Clearly, this is not a full clinical viewer, but it's a way to quickly see where things where things are. And this, by the way, is also coupled with a series of tools that are freely downloadable to integrate that with DICOM images and PACS systems to do all the pre-processing and quality assessments. Okay, so second project is where we are trying to leverage radiology reports with imaging data. As you know, for creating artificial intelligence models, we need labels, high quality labels, and this is a major hurdle, especially in medical imaging. Okay, this is because the annotations is a manual, time-consuming process, is expensive in state medical expertise. But what is often forgotten that labels are often not always black and white. So give a precise information as, oh yes, this person has X versus then Y, is not as obvious. Okay, and this is as we saw before, it's a problem. So what is the opportunity? We have imaging databases or PACS that do store radiology reports as part of the clinical care. So what if we could use this information to pre-train imaging models with very large data sets and no manual labeling, apart from matching with the reports, to create deep learning foundational models that are specialized for for something like acute stroke and imaging. So this is what we started doing. So we started with CTA images and reports. So we have a first pre-training step in which we try to map imaging and reports together, but by making sure that the distance between the imaging and the report is as close as possible in feature space, using an extension of what's known as clip-based loss. And then once we have a pre-trained model, we can use this pre-trained model to adapt to any task about acute stroke that we want with a lot less data. Also note that this is the first time it's done in these projects with 3D medical imaging, and the reason is because current artificial intelligence models, they are typically used to the images and are based on natural images. So whenever we try to translate these to our environment, there are always challenges. So this model starts from zero, which is great because it doesn't have any information about things that might be common on natural images but are not common in here. So here is so we had this paper published with a smaller data set, but now we are moving forward and we are doing this with multiple tasks. So in here you have an example of a 3D deep learning architecture trained from scratch in these dotted lines versus the same architecture that has been pre-trained with the radiology reports data set using a data set from completely different sites. Okay, and on the y-axis you have the AUC. On the x-axis you have the percentage of subjects that have been used for training. Here we have 3 tasks. The model is essentially the same. And the first one is for detecting large vessel occlusion, second one for detecting hemorrhagic stroke, and the third one is to detect if the ischemic core is larger than 50 milliliters. And you can see how these methods, with training, it's essentially always better, but especially when these days when the data is lower and lower and lower, which is great. So some conclusions. This is the first example of a single imaging pre-trained CTA models adaptable to multiple acute stroke tasks. And then supervised learning using radiology reports is a very untapped resources, especially in medical imaging. This gives us a unique opportunity to create general purpose imaging models that can be adapted to very specific tasks with much less data and generalizable across sites. So because of that, we are in the process of running this type of models with a large data set, thanks to the collaborations with Memoria Herman. We have a total of 24,093 subjects right now in our servers. I think we have around 12,000. We, as you know, in Texas, in Houston, we have a very good distribution between the race, ethnicities, and multiple sites. And then we're gonna create a series of benchmarks for acute stroke relevant tasks to see how these foundational models works. But the most exciting part, really, I think, is that these foundational models will allow researchers in the medical school or everywhere really in the world to try out new hypotheses. So if there are, I often get contacted by potential collaborators that ask me, oh, what about if we could test these specific outcomes if we try in this subset of patients. And what happens is that these subset of patients, they are very, very, very low numbers. So doing advanced AI is difficult. But if we had a foundational model specialized on acute stroke, that is possible. So we had, for example, a model that was trained for a very specific outcomes with just 40 people, and that was enough to test our hypothesis. And then third, another project in which we are coupling retina imaging to use as a proxy for CT imaging in stroke care. And the unmet medical need that in here is based on the need of mobile stroke units. So we know that mobile stroke units are ambulances with CT scanners, and when they are used, they are extremely effective because they can essentially tell if someone has an acute stroke and if there are no hemorrhages, so that TPA can be given immediately. They are, however, incredibly expensive and really are unlikely to be widespread around the country. So what if we had a portable and expensive system to act as a proxy for CT? And this is what we're trying to do. So we're gonna we try to use retina imaging, specifically fundus images and OCTA, as a proxy for what you would get with the brain CT. Why? Because the retina vasculature is directly connected to the brain, and it might have the same similar information of what we could get from with the CT images. And we saw with our preliminary results, with 88 subjects, in which we had 15 acute stroke patients, 70 controls, that by using OCTA plus a machine learning algorithm, we could distinguish them pretty well. Okay, so and then because of that, we showed essentially that CTA appears to be feasible to act as a proxy. Now there are other steps to take, like detecting if there is any hemorrhage, and then making sure that these systems are usable with people that are not that are not very collaborative, but the technology essentially is there. And we also created a live demo of the model that is available on the internet, so people that have these systems can put in the variable, and then they can stand on the probability of having stroke or not. So I would like to thank all of my lab. But especially a special thanks to all the collaborators at the medical school and at the School of Biomedical Informatics. Without it would have been possible to do all of this work. So thank you very much.